Okay, my name is Richard, and I am a master's student at the Edinburgh Performance Computing Centre, which is part of the University of Edinburgh. And for my dissertation, I'm looking at the optimization of HPC libraries using RISC-V technology. So for this, I'm specifically been looking at utilizing the RVV vector extensions within RISC-V. For this talk, I'm not going to give any source code examples, but they are available from my GitHub, which is here. So people will be able to check that out if they look at the slides later. If you are planning on using SIMD, I suggest you look at yesterday's talk from Andreas, who gave a great talk on portable SIMD, which is much more usable for cross-platform development. But I was using specific instructions because I was looking at the performance of the instruction sets on different architectures. So a year ago, in preparation for my dissertation, I looked at using Rust as a core language for examples, but with the RISC-V systems that I had available to me, Rust was not particularly stable, so I used C. So moving on a year to around Easter time this year, I had a Banana Pi F3 running Fedora 42, and Rust was running very nicely on this, so I thought I'd give it another go. So I plan to implement a gem-like function using AVX, Neon, and RVV to compare the different performances of these architectures. So starting off, I wrote a scalar version of the code to give a baseline for timings. And then my home computer uses AVX2 with an AMD processor. So I coded up the AVX2 version. So at the top of the Rust code, we put in the use standard arch x8664 line, and this gives us access to the AVX2 instructions. AVX and other instruction sets for the vector instructions on CPU are regarded as unsafe by Rust because you can't guarantee them being available on all systems. And then the final step is we add in a .cargo config toml file with Rust flags -c target CPU native. So this line tells us that we are targeting the CPU in the machine we are compiling on. I also used Rayon for multi-threading. So for testing the performance of my newly written gem function, I multiplied together two 1024 by 1024 arrays filled with random numbers. AVX does lose precision when processing. It's not fully IEEE compliant for floating point maths. So we add in some tolerances for the comparison of results between the scalar and SIMD code. But with our first run-ins, as we see, I'm running F32 and F64 versions. If you notice with the F32 versions, scalar with Rayon gives us around 7.8 times speed up. And then the single-threaded vector instructions give roughly the same performance increase, but combining them together gives us a very nice increase, resulting in a 51 times speed up for this gem operation on a 16-thread processor. Next up, I have access to an Oracle ARM cloud computer, so we add in the Neon version of our gem code. So at the top of the code, again, we're using the standard arch AArch64 this time to get the Neon instruction set. But because I'm wanting to use a single code base for both architectures, we've got these two lines here, the config target arch, and we put these before each of the functions that are specifically targeting an architecture. So when we compile, the compiler knows which code to use and which to ignore. Neon is an older vector instruction set. It's got a vector register size that's half that of AVX2. But you can see we're still on this 4-thread CPU, we're still getting some nice optimization going on with 26 times speed up for the F32. So next up, AVX512. This is Intel's newer version of AVX. This gives us a 512-bit vector register, but it's not natively supported in the stable version of the Rust compiler. So we have to change our Rust compiler to use the nightly build and then add in these 2 lines here to say the features we're wishing to use in the nightly build. But then stop press, we hit the 9th of May this year, and AVX 512 is included in the stable Rust C compiler. So we ignore the previous slide, we go back to the stable compiler, and we remove those 2 target arch lines that we'd inserted. The next interesting quirk of this is a CPU that has AVX 512 also supports AVX2. So in our source code, dividing up how the compiler is going to choose which code to use, we're now, if it's AVX2, we're actually saying if there's not the AVX 512 feature, we're using AVX2. But if there is, we're using AVX 512. This is not the best solution. It works for my examples. But if you've got a CPU that only uses Intel with SSE, this would fall over and not work. So it's slightly contrived, but it works for the example. But now we see the true power of AVX 512 on this nice Intel Xeon 52-thread computer. We are seeing speedups in F32 of 161 times. So we're going from 1.16 seconds to 7.22 milliseconds. And that's the kind of speed ups we like to see in high performance computing. That's saving you money if you're having to pay for computer time. And it's allowing you to do a lot more with the available resources. Now, the title of this talk included the word pain, and so far it's been going pretty well. But then we get to our RISC-V RVV 1.2 machine, the Banana Pi F3. The initial issues with this were the support for RVV within the Rust compiler. I was unable to get it to work in the same way I had with Neon and Neon and AVX. I had a quick experiment with using inline assembly, using the Rust ASM command, and I was tying myself in knots. So I gave up. I've already written a C function for my dissertation for dot, which is the core of this gem system. So we use the C code instead. So if you're using C code for this kind of thing, we need to add in the build dependency sections in the cargo.toml file. This gives you access to the build flags you want to pass through to your C compiler. Using C rather than Rust slightly defeats the point of this Rust experiment. So for my dissertation, I will still be primarily using the C code examples. Now, because we're using a C function for RISC-V and we're using the Rust functions for all the other architectures, we need to divide our code up, again, using this target architecture command and dividing up between sections for RISC-V and sections for not RISC-V. The code now runs and builds on the 4 chosen architectures and is stable, but it's not as neat as it had been before we added in RISC-V. As you can see, RISC-V is not a high performance option at the moment with my Banana Pi machine. It is rather lagging behind the options from AMD, ARM and Intel in performance. But you can see we are still getting some nice speed ups, and this has got potential for when the general processor architecture does catch up more to the kind of performance we see on Intel, ARM and AMD architectures. So in conclusion, you can get some very, very good optimization with certain workloads within Rust using vector instructions. the AVX 512 really does stand out beyond the Neon and AVX2 and RISC-V. So if you are able to target that processor, you're getting some great optimizations. I've not been able to get a machine to play with ARM SVE2, which is their newest vector instruction set. And sadly, my dissertation is about RISC-V, and this just didn't cut the mustard, I'm afraid. So it's been an interesting delve into what Rust can do, but sadly, in the end, that was it. So that's my experience, and there we go.
Thank you very much. Your results will look very promising. There is a question in the chat and one in Q&A.
Yep.
So the question in the chat says, is AVX really not IEEE 754 compliant?
You can add in build flags in with the C compiler. I'm not sure out through Rust. So you can add in compatibility to make AVX compliant with IEEE standards, but it does then slow your operation down. So you're balancing out here. If your code really does need that IEEE accuracy, you need to add in those build flags, and you will slow down the potential of what AVX can offer. If you're not so worried about the precision, then you don't add that in, and you get some nice speed ups.
Nice. There is another question in the Q&A. It says, Rich, do you know if the Portal SIMD supports or will soon support RISC-V?
The which, sorry,
the Portal SIMD.
Oh, okay. I wasn't aware. I've not delved into the portable SIMD that much, but it'll be great once RISC-V is in there, because then you won't need to mess about in your source code with all these things that I've been demonstrating here of how you have to divide your code up to make sure the compiler is only targeting your current processor.
Okay. Well, there's another one. It says, can the Rust compiler auto apply these optimizations?
Mm-hmm. The which, sorry,
the Rust compiler.
The Rust compiler will.
It's on the Q&A. It says,
oh, I've not got access to the Q&A bit. I can't see a.
It's on the bar.
Oh, sorry. It's under the more thing. There we go. I believe it does. It can, but because I'm specifically comparing different architectures, I want to know that I'm using the specific commands for those architectures, and I'm comparing like with like. If you're using the compiler auto vectorization options, I'm not sure what they're doing. So because I'm specifically looking at the performance of the instructions, I opted to use the more brute force putting in the actual instructions via the intrinsics and commands for those different architectures.